Okay, so in this question, we think about what we know about sine squared uh, x and cos squared x. So if we start off by thinking about sine squared x, so sine x is between -1 and 1. So if we square it up and think about what would happen, we're going to get 0 is between sine squared x and 1, and the same with cos squared x. Now, from there, it's reasonably straightforward to work out the rest of this question. So we can say that 2 sine squared x must be between 1, because 0, when this part, when sine squared x is 0, we get 2 to the power of 0, which is 1, and between 2. So somewhere between 1 and 2. Same thing will happen for 2 cos squared x, and between 1 and 2. So the only way that our function at the top can equal 2 is if sine squared x and cos squared x equal 0. Now, we know that sine squared x plus cos squared x is always equal to 1. Therefore, this has no solutions because they can't both equal 0 at the same time. Okay, so what we're going to do on this question is, first of all, think about the shape of what this graph looks like. So the shape of the graph is a positive quartic, so we're going to have something that looks a little bit like this. So the key thing is that we're going to notice that we need to have the two minimum points need to be below the x-axis. The one maximum point needs to be above. So we're talking about maximum and minimum points. We're going to start off by differentiating this. So we're going to get 12x cubed minus 48x squared plus 36x. And we're looking for the turning points, so we're going to put it equal to 0. We can then factorise this quite nicely. There's a 12x that we can pull out. We're then left with x squared minus 4x plus 3 equals 0, which then gives us 12x, x minus 3, x minus 1 equals 0. And we've got our three solutions then. Our x equals 0. Sorry, I've missed a little x out here. X equals 0, x equals 3, x equals 1. Now, if we think about where they're going to be, so if we're going along, we're going to have our first root is going to be 0, which will be this one here, which will be our minimum on the left. Next one along is 1, which is going to be a maximum. Next one along is going to be 3, which would need to be our minimum. So we need to have this as a min, this as a minimum, this as a max. And we want, for us to have four real solutions, our two minimums to be less than 0 when we sub them back into the original function, and our one maximum to be above 0. If we start off with 0, we get 0 minus 0 plus 0 plus k equals 0. So we want k needs to be less than 0 for us to get our minimum underneath the x-axis. Next one with 3, a little bit more complicated. We're going to get 2, 4, 3 minus 4, 3, 2 plus 1, 6, 2 plus k equals 0, which if we work that all through gives me k minus 27 equals 0. Now we want this to be below the y-axis, so we want k to be less than 20. Oh no, sorry. Drop this out. We want this to be negative, so k needs to be less than 27 here. Our maximum okay, so now if we look at our maximum, if we substitute in 1, we get 3 minus 16 plus 18 plus k equals 0, which gives me k plus 5 equals 0. So that gives me k. We want this to be is the maximum, so it needs to be greater than 0. So k needs to be greater than, sorry, k needs to be greater here than minus 5. So we need to have k less than 0, k less than 27. So this k less than 27 becomes redundant because we need it to be less than 0 and it less than 27. So we can almost ignore this. We need k to be greater than minus 5 and less than 0, which is going to be this one over here. It's going to be D. Okay, so our answer to F is going to be D. Okay, so this is, I thought, quite a tricky question. I think it's quite important with math papers to know that I can't just go through. I wouldn't get 100% on on any of the math papers, I don't think. So sometimes I do look at the question, I'm not really sure. So I had to look up the solutions for this question. It's quite a nice question actually, in terms of what it's testing, but it's sort of done it in quite an odd way. The things that we're looking at really are that if we've got a function sine x, when does the values of sine x equal each other? It's going to equal sine x of x plus 2 pi. So that's one case of when our y values are going to be equal. So we can say then that our y is going to equal x plus 2n pi. Now 2n pi is going to be something that we can add on. So that's going to be changing our y-intercept. If we're looking at this, our gradient is going to be a positive gradient. So we can have any of the graphs, A, C, and D. So we know it definitely can't be B because that's just got negative gradients on it. But we've got lots and lots of parallel lines that are of this form. Now the other time when our sine graph equals each other is when we say sine x equals sine pi take away x. So if we're thinking of in degrees, to find our second solution, we do 180 take away pi. Now that's going to give me y equals minus x plus n pi. So there are two lines that we could have. Now if we think about what we did on the last one, we talked about it being a positive gradient. This one has got a negative gradient. So this graph would be either B or C. Now the only graph that's got positive and negative gradients on it is going to be graph C. So graph C is the one that's going to map all of the solutions. Like I said, that was quite a tricky and involved question. So don't worry hopefully me talking it through has made sense, but don't worry too much if you don't think that's particularly an intuitive thing to spot. Right, I was one I think that you didn't fully get, so I'm just going to talk through a little hint on how you can make a start on this question rather than me going through and doing everything for you. So the key thing is that it's saying x squared minus 1 is a factor. First thing to notice with x squared minus 1, this is quite important to notice on math papers, is x squared minus 1 equals x plus 1 x minus 1. So we should be noting that we've got a difference of 2 squares, and that then means that x minus 1 is a factor, x plus 1 is a factor. Now what that would then tell me to do next is to be substituting in x is plus 1, x is minus 1, think about your factor theorem. And if it's a factor, when you're substituting 1 and minus 1, it should both be equal to 0. When you do that, it will then come out some quite nice maths in that. But I'd like you to have a go from there, working through that rest of that question. Okay, this one again, like the last question, is something that's really important to spot. If you've got like an x cubed, an y cubed, we've got x squared y and xy squared, that to me suggests we're going to have something that can be factorized into a cubic. So this one is going to factorize to x plus 2y cubed equals 2 to the power 30. Now from here it's then reasonably straightforward for you to start to think about what to do next. Well, not straightforward, but that's the key bit to making a start on that question. So I'm just going to stop here again on this question and let you have a think about what you would do next to finish off your solution to this question. Okay, so on this question you picked up pretty much all of the marks on 1 to 4, and the only thing we found difficult was question 5, which is when you said you didn't really know how to make a start on. So essentially the way we're thinking about this is we've got this curve and the point Q is AA squared. So Q is just sort of, as A varies, is just sort of any point on our curve C. So we're looking for a point that's not on C, because it would just be sort of obvious if it was on C, where RQ, so R to a point on the curve, is unique for a value of A. So if, say, for example, we took a point here, this wouldn't have a unique solution because the distance here and the distance here would be the same. So it'd be this value of whatever the x value is here, and whatever the x value is down here would be the same. So we need to find a point where the distance to the curve essentially is only going to have like one solution that's going to be the closest rather than two. So essentially we can't have any points that are inside our parabola, anything on the outside, so any point sort of around here, any point around here, anything down here is going to have a solution. So I would just pick something simple to justify if we extend our axis down here and just pick a point down here. So we could maybe say R equals like 0 minus 1, 0 minus 2, and then we're going to have just to the minimum points, it's a 0, 0 is the shortest. Anything else for the curve is going to be further away. So I'm not going to write out exactly what I'd say to justify my answer, just because it's a bit tricky to write on the tablet on the screen, but that's sort of a loose explanation of how we would pick up the final marks on that question.